Hello everybody, this is Dr. Mel Beatty, and today we'll be going through medications that affect the renin-angiotensin pathway. At the end of this lecture, I would expect you to be able to describe the mechanism of action of those drugs and be able to explain the structure-activity relationship between the drug molecules and the receptors. And finally, there are some key structural components of the ACE inhibitors, angiotensin receptor blockers, and aliskiren. I think I'm missing an I here, which is a renin inhibitor. So there are some key structural components that I would like you to be familiar with. And we'll go through these during the lecture. You have an accompanying handout that was posted as well on the website that will allow you to take notes and fill in the blanks as you go through the presentation. All right. So the renin-angiotensin pathway is a very important pathway. It helps regulate blood volume, and in regulating blood volume, it also regulates blood pressure and electrolyte balance. So there are two main enzymes that are involved in the renin-angiotensin pathway. There is renin and angiotensin converting enzymes. Now those enzymes work together to sequentially cleave angiotensin 1 to beginning with angiotensinogen, cleaving it to angiotensin 1, then to angiotensin 2. And the next slide actually has a clear scheme of how these enzymes function. So renin is an aspartyl protease enzyme. It's a very specific enzyme. It is substrate specific, okay? So it's going to cleave the leucine-valine bond in angiotensinogen. And that's going to lead to the formation of angiotensin 1, okay? So renin is going to cleave the leucine-valine bond in angiotensinogen to give you angiotensin 1. Now, again, it is substrate specific and it's the rate limiting step in the conversion of angiotensinogen to angiotensin 2. Okay. Now, ACE is a non-specific enzyme. It's an enzyme that's going to cleave substrates that contain a tripeptide sequence. So it's not as specific as renin, and we will see how that non-specificity leads to some side effect. It is a dipeptidyl carboxypeptidase enzyme, and it contains a zinc that is very important for the activity of the enzyme and of the ACE inhibitors. Now, because it's non-specific, ACE can also degrade other enzymes such as bradykinin. Now, bradykinin is involved in many processes such as vasodilation. It's involved in vasodilation and also in bronchoconstriction. Constriction. Okay. It's also involved in stimulation of prostaglandin synthesis. So prostaglandin synthesis, which is going to be involved in inflammation. Okay. Inflammation. And obviously increases vascular permeability, which also is going to increase the effect of inflammation. Now, when you take a look at some of the ACE inhibitors on the market, they often have a side effect of a dry cough. That dry cough is because of the fact that it can cause bronchoconstriction. When those ACE inhibitors are taken, they actually also degrade bradykinin, and that's going to lead to bronchoconstriction. It's going to lead to prostaglandin synthesis and increase vascular permeability. So it leads to that dry cough that we see. Now, the compounds that inhibits the effect of renin, ACE, and angiotensin 2 will then have an important role to play in the control of hypertension. And there's other conditions that those compounds also play an important role in. So this slide has a lot of words. Let's go into one that has mainly structures and a scheme that I'm going to show you. So beginning here, we have angiotensinogen, and as we mentioned, renin is the enzyme that's going to cleave angiotensinogen between the leucine and the valine. Again, it's very substrate specific, okay, and it's the rate limiting step. In the conversion of angiotensinogen to angiotensin 2. All right, so renin converts angiotensinogen to angiotensin 1, and once it's converted to angiotensin 1, ACE then is going to convert angiotensin 1 to angiotensin 2. So ACE is going to then cleave between the angiotensin converting enzyme is going to cleave between the phenyl and the histidine here and lead to the formation of angiotensin 2. Now there are some aminopeptidases that are available in the body that are then going to process angiotensin 2 further, cleaving at this position here, and lead to the formation of angiotensin 3. Now angiotensin 2 is a very powerful enzyme that leads to vasoconstriction. It leads to the release of aldosterone, which then is going to lead to water and sodium retention. And so you can see how all those factors put together will actually increase blood pressure and lead to hypertension. And also sodium water retention always is going to lead to increased blood volume. Okay, I hope this makes sense to you. So quickly again, sequentially, renin and angiotensin converting enzyme are going to process angiotensinogen first to angiotensin 1, then to angiotensin 2. Angiotensin 2 is a very powerful enzyme that leads to vasoconstriction, release of aldosterone, and water sodium retention. When the water and sodium is retained, it leads to an increase in blood sodium, which leads to an increase in blood volume, which then results in increase in blood pressure. Now, the first class of drugs we'll take a look at will be the angiotensin converting enzyme inhibitors. Now, angiotensin converting enzyme inhibitors are drugs that are used in the treatment of hypertension. They basically prevent the angiotensin converting enzyme from converting angiotensin 1 to angiotensin 2. Okay, so they block the conversion of angiotensin 1 to angiotensin 2. Now, there are three classes of drugs in the ACE inhibitors. There are the sulfhydryl containing drugs. They are the dicarboxylate containing drugs and the phosphate containing inhibitors. So we'll take a look at those three classes of drugs in the subsequent slides. Now, those drugs are going to block the ACE enzyme, and the way they do that is they're going to interact with the ACE enzyme in three specific ways, at three specific sites in the binding pocket. If you look at this scheme here, and I have it written in words here, but if you look at this scheme on the right side of the slide, there is a cationic site. There is a cationic site where the anionic carboxylate, which is here, the anionic carboxylate is going to interact with lysine and or arginine here. So it's going to interact and binds. So the cationic site is going to interact and bind to the anionic carboxylate, and usually the amino acids that you have there are either lysine or arginine. Okay, so a cationic site where the anionic carboxylate terminus of the peptide substrate binds to. So it's this right here, cationic site, ionic site. Okay, in this region. Then there's a zinc that's present inside of the binding pocket that's actually going to stabilize the tetrahedral intermediate. So when you look at the binding pocket here, there is a zinc that's present, and that zinc it works with a water molecule to then allow for through a series of interaction, it allows that water to attack the carbonyl of the carboxylic group that's here and lead to the formation of a tetrahedral intermediate. Once the tetrahedral intermediate is present, you can see that this zinc here is going to have an ionic interaction between the negative charge on that oxygen here and the positive charge of the zinc. So the zinc is very important in stabilizing the tetrahedral intermediate that is formed as a result of the water attack on the carbonyl carbon. Okay, so zinc is the second place where the reaction zinc is the second binding pocket, or the second element of that interaction between the ACE inhibitors and the enzyme. And finally, there is a hydrophobic pocket. There's a hydrophobic pocket where and that hydrophobic pocket is specific to hydrophobic amino acids. So you're gonna have aromatic amino acids, you're gonna have non-polar amino acids on the C terminus. So the hydrophobic pocket is right here in this region here. Let me just go down here, right here in this region. Okay, so here we have leucine that is in that binding pocket here. Now, so this is an idea of how those ACE inhibitors actually interact with the inside of the enzyme. Now, on exams, I've been known to provide the structure of a ACE inhibitor and then give you a matching question asking you match. Let's say I call this portion here. Let's say I call this portion of the enzyme. Let's go to the next slide. Maybe I have a. Okay, so let's say I call this portion of the enzyme. So I have something like this. I have zinc. I have cationic binding site. And then I have hydrophobic pocket. Okay, that's on one side. And then on the other side, I have this region here that I can call A, this region that I can call B. Okay, I can call this region here, I can call that region B, and then this region here that I can call C. And then I ask you to match A, B, and C with the proper region. So here, C will be the carboxylate. The carboxylate is going to be interacting with the cationic region. Okay. B will be the proline there. The proline will be interacting with the hydrophobic pocket. And A will either be carboxylate, will either be sulfhydryl carboxylate, or a phosphate derivative. Okay, and these interact with the zinc cation there. Okay, all right. So yeah, and this slide is also a good slide that shows you a difference between one that's a sulfhydryl group here and another one that's a carboxylate derivative. Now, when you look at drugs that interact with an enzyme, there's many different ways to develop those drugs. One way is to make those drugs look like the substrate. Another way is to make those drugs look like the intermediate, and another way is to make the drugs look like the product. Okay, I'm not going to go too deep into those classifications here, but this is a concept that needs to be remembered. And alaprelide, for instance, is designed to look more like the transition state inhibitor as opposed to captopril. Another thing to note here, the sulfhydryl group actually has a higher affinity to the zinc, and Captopril is actually it's a really potent drug. The issue of Captopril is the sulfhydryl group tends to form disulfide bonds, and in forming the disulfide bonds, it basically inactivates the drugs. So it was a very good drug that was designed, but it has a very short duration of action. Another issue with Captopril is the fact that the sulfhydryl group actually leads to side effects. So a lot of patients are not able to take that drug because of either the side effect or it has a short duration of action. So more intentional design was done to move from the sulfhydryl group into either the carboxylate or the phosphate groups. Because the phosphate groups and the carboxylate groups don't have the same level of affinity to the zinc, then you can notice in a lot of these new drugs you actually have more groups that are added to the molecule, such as in this case, for instance, you have another hydrophobic group that's added here, and in the other drugs that I show you, you'll see that we start to increase the number of amino acids actually to make sure that there is stronger binding to the binding pocket. Okay, so quickly here to remember on this slide, first thing, enalaprilate looks more like the transition state. Okay, second thing, Captopril was one of the first that was designed using the sulfhydryl group. The sulfhydryl group has a high affinity to the zinc. However, because it dimerizes and gives you disulfide, it inactivates the drug. So Captopril has a shorter duration of action, a short half-life. In order to improve on the ability of the drug, then carboxylate and phosphate groups were introduced in ACE inhibitors. And lastly, as far as Captopril is concerned, because of the sulfhydryl group, you have a lot of side effects that are linked to that sulfhydryl group, which is another reason why carboxylate and phosphate containing ACE inhibitors were designed. Let's dive a little deeper into the structure activity relationship of these ACE inhibitors. Okay, let's run through the structure activity relationship of these ACE inhibitors here and add a little more to what we've already talked about. So the ACE inhibitors require a nitrogen containing ring, okay? And that nitrogen containing ring needs to have a carboxylic acid attached to it for binding to the cationic site of the ACE enzyme binding site. It is to note that large heterocyclic nitrogen containing rings increase the potency. So the larger the heterocyclic binding nitrogen containing ring, the higher the potency. Second thing here is zinc binding group. The zinc binding group can either be a sulfhydryl containing group, can be a carboxylic acid containing group, or can be a phosphate containing group. Okay. Now the sulfhydryl group has the highest binding affinity to the zinc. However, the sulfhydryl group also have highest incidence of rashes, loss of taste, and they form disulfide bonds, as I've mentioned in the previous slide. The disulfide dimers lead to the activation of the drugs, and those drugs have shorter half-life. Okay, so the carboxylate and the phosphonate groups are also able to bind to the zinc, and those inhibitors actually mimic the transition state of the peptide hydrolysis reaction. Now, if you notice here, I've mentioned that X is often a methyl group. Oftentimes, X is a methyl group. Now, something to remember, when the name ends with pril, it's an ester, okay? And it's done to make the drug more bioavailable. When the name ends with prilat, it's not an ester, it's actually the active drug. So let's move on from here. It's an important fact, and we'll take a look at it in the coming slides. When we look at the physicochemical properties that affect the pharmacokinetics, the first thing to remember is that most of the ACE inhibitors are amphoteric, meaning that they can have both basic and acidic properties at the same time, except for captopril and fosinopril, that are both acidic. So captopril and fosinopril are both acidic. Now, when in this structure here, I show a Zwitter ion. A Zwitter ion is when a molecule can have both positive and negative charge at the same time. Obviously, positive charge because this is the basic part of the molecule that's actually going to be protonated, and negative because this is the acidic part of the molecule that's going to lose a proton. So you form a Zwitter ion. Because of the fact that they're acidic and basic, those ACE inhibitors have most of them are they have hydrophilicity. However, they also have good lipid solubility. Okay, they have good lipid solubility, except for captopril, enalaprilide, and lisinopril. Okay, they have good lipid solubility except for captopril, enalaprilide, and lisinopril. Now, again, basic and acidic means that they are also hydrophilic, but lisinopril is the most hydrophilic of the ACE inhibitors. Okay, it's the most hydrophilic, and it also has good bioavailability. Now, all this information here is good. What I really want you to remember from this is the fact that they are both basic and acidic, and they have overall good solubility. And be able to tell me what a Zwitter ion is and what amphoteric means. So let's zoom in on those structures. And on an exam, drawing any of these structures, I would expect you to be able to point out to me which one of those parts of the molecules are actually going to interact with the binding site. So let's take a couple of them here and see if I can give you a good idea here. So for instance, here you have enalapril. Remember we said enalapril, if it ends with pril, it's an ester. Okay, and I know that it's written in a way here where the oxygen is connected to the carbon, but it's really like this: CH2 CH3. Okay, CH2 CH3. And then inside of the body, what will happen is you're gonna have water hydrolysis probably, or any kind of nucleophile that will come in and attack at this position here, causing the electrons to go up, and then this is going to lead to the loss of this molecule here. So you're going to end up with, and this is the part of the molecule that is connected, you're just going to end up with a carboxylate at this position with a negative charge. Now this carboxylate at with the negative charge is what's going to be able to interact with the zinc. Okay, it's going to be able to interact with the zinc. So let me use a different structure here. This one here, and lisinopril, I want to say lisinopril is an exception to the rule. Lisinopril, it already has a carboxylate here, but all the other ones, enalapril, benelapril, when you see a pril, it's usually an ester. Okay, benidopril, it's usually ester. When you have prilat, is the active drug. Okay, so anyways, let's keep moving here. So here, this portion here will be able to interact with the zinc. This will be the hydrophobic binding pocket, and this inside of the body is actually going to be lose its proton because it's acidic, and it's going to be able to interact with the cationic binding site. Okay, let's do the same exercise here. Inside of the body, this is going to break off to leave you with, so this is going to break off, be cleaved off by esterases, and give you a negative charge that will be able to interact with the zinc anion. You will have the hydrophobic interaction here, and here cationic binding site. Okay, let me just do one last here so that you get the concept. You have zinc, hydrophobic, and you're going to have cationic binding site here. Okay. All right, let's go to the next slide. So now we'll take a look at the metabolism of some of these here. We've already mentioned the disulfide dimer that happens with Captopril, and it's important because it reduces the activity. It basically deactivates the drug. Okay. Then benazepril can actually undergo glucuronidation and be excreted that way. And ramipril can also undergo cyclization. So these are some interesting type of mechanistic, some interesting type of metabolism, mechanism of metabolism that I would like you to know. So for captopril, it's the disulfide dimer. For benazepril, it's the glucuronide conjugate. And for ramipril, it's the cyclization. Okay, so these are things that will be good for you to be able to remember and understand as you go through these lectures here. Now we're gonna jump into angiotensin 2 receptor blockers. So those specific drugs here block the action of angiotensin 2. They block the action of angiotensin 2 because they actually compete for the binding site of the angiotensin receptor. Now there are two subtypes. There is angiotensin receptor 1 and you have angiotensin receptor 2 subtype. Now the ARBs are 10,000 times more selective for the angiotensin receptor 1 than the angiotensin receptor 2. They were designed actually intentionally that way because angiotensin receptor subtype 1 actually affects vasoconstriction. Okay, it also affects aldosterone and vasopressin release. Angiotensin 2 has cardioprotective effects. So they were designed on purpose to mainly affect angiotensin receptor subtype 1. Now when we take a look at the structure activity relationship, those drugs are actually peptidomimetics. They are peptidomimetics, and the pharmacophore that's used for the design of those drugs is a 1-benzyl 5-acetyl imidazole pharmacophore. Okay, 1-benzyl 5-acetyl imidazole pharmacophore. This is the imidazole group here. The benzyl is at this position, and then the acetyl is at this position here. Okay, now so when we talk about peptidomimetic, it basically means that the pharmacophore mimics key amino acids residues. It mimics key amino acid residues. In this particular concept here, it's going to mimic isoleucine, and we have the equivalencies here, the arrows that show you which part of the molecule mimics which amino acid. So isoleucine is going to be mimicked by this aliphatic chain here. Tyrosine is going to be mimicked by the aromatic ring at this position, and you can have different R2 groups here. The histidine is going to be mimicked by the presence of the imidazole, and additional functional groups can be added to mimic more of these amino acids here. But this is the basic pharmacophoric structure, and obviously the carboxylate group here is going to mimic this carboxylate group at this position here. Now let's dive deeper into that. The R group can be either hydrogen or chloride. Okay, the R group that's here can either be hydrogen or chloride. The carboxylic acid moiety can be replaced by any other type of hydrogen bonding capable moieties. Okay, so the carboxylic acid moiety here you can put any other type of hydrogen bonding moieties. In some cases, you will only see OH, but anything with hydrogen bonding capability can be used to replace the carboxylic acid. And then the R2 group can either be carboxylic acid or any O substituted phenols. So this is the R2 group here. Can either be a carboxylic acid or any O substituted phenols. Okay. So when you talk about designing peptidomimetics, there's basically three basic steps. You have to identify the amino acid sequence that's involved in the action. So you have many amino acids in those proteins, but which one is actually involved in the action? Which one causes the activity? Once you have the sequence of amino acid, then you have to determine the spatial, I put special here, but it should be spatial arrangement of the amino acid residues. Once you have the spatial arrangement, then you use a template to mount these amino acid residues. And then you can use key bioisosteric replacements to substitute for these amino acids. For instance, we've talked about how tyrosine is replaced here by the aromatic ring. We talked about how the carboxylate group here can simply be replaced by any hydrogen, any group that can participate in hydrogen bonding activities, and how the histidine is replaced by the imidazole ring here. Okay, so you find out the amino acids that are actually needed. Once you find the amino acid, you determine the spatial orientation. Then you use a scaffold or a template to mount those amino acids on that template, and then you do bioisosteric replacement where possible. Now, the physical chemical properties that affect the pharmacokinetic of these drugs. ARBs are acidic because you have the carboxylate that's present, and you also have, and you have to think about it this way: when they're designed, when they are administered as the acidic drug. Okay, when they go inside of the body, then they become they lose their proton and they become the carboxylate, but they're actually carboxylic acids that react inside of the body to become carboxylate. So they're acidic for that very reason. You have this group here that's acidic, carboxylic acid, and you also have a tetrazole group that brings acidity to that group. Now, they have a certain amount of lipophilicity as well, because as you notice, not only do we have a aromatic side chain here, you also have an aliphatic side chain here. So the tetrazole ring containing ARBs are more lipophilic and have greater binding than those without the tetrazole ring. That's important to remember. Okay. Now, quickly here, these are not things that I will test you on, but it's good for you to know that they can all be taken with meals. But most of them have low but adequate bioavailability, so you can take it with food. Half-life allow for once or twice a day dosing. Most of them are going to be eliminated through the fishes, no dosing requirement is needed in renal impairment. So this is just put here for your knowledge, but I will not quiz you specifically on these things. I will leave that up to the pharmacy practice part of the class. On this slide here, I have a few examples of ARBs, and I just wanted to go through the same exercise we went through with the ACE inhibitors. So given this structure here, what I will ask you, for instance, is which structure mimics what amino acid? Okay, which structure mimics what amino acid? Or what types of bioisosteric replacement took place here? So this carbonyl group here is there for the carboxylic acid portion. Okay, it's there for the carboxylic acid portion because it can undergo hydrogen bonding activity. Okay, now normally we will have a tetrazole or an imidazole types of structure here to mimic the histidine. In this particular case, we have that structure here. I want to bring your attention to the fact that although it's different than this molecule here, it's a simple bioisosteric replacement. Okay, so you still have those two nitrogen groups here. Okay, they're separated by the same number of carbons. So you have nitrogen, 1, 2, 3. Okay, you have the, so 1, 2, 3 position, you have a nitrogen. If you start here, 1, 2, 3 position, you still have a nitrogen. The aliphatic side chain is still at position 2. Okay, aliphatic side chain is still at position 2. This here represent the R group that's here. You have this R group that's here. All right, and you still have the phenyl substituted component here, still on the nitrogen. So they may have slightly different structures, but for the most part, they follow the same pharmacophore. They follow the same pharmacophore. Okay, we can go through the same exercise here. Now you look at this here. This doesn't have the nitrogen, but when you look at it, the way it is designed, the nitrogen here is connected to the carboxylic acid portion. Okay, and then if you actually wanted to count this actually can pretend to be a ring or look like a ring, although it's not connected. Then this is more of a classical one. Losartan is more of a classical one where you have the hydrogen bonding, meant to write H not K, hydrogen bonding capable group here. You have the R group, that's a chloride. You have the aliphatic group here. You have the benzyl substituted group at this position here, and obviously you have this group that's substituting for the histidine. Okay, so you can go through the rest of those and look at how those structures actually still maintain the pharmacophoric requirement to be good ARBs blockers. Most of the ARBs are eliminated unchanged. Losartan is metabolized by CYP2C9 enzyme and 3A4 to an active metabolite. So that's important to note there. And so it's metabolized to give you an active metabolite. And then I mentioned here as well candesartan and some other ones that are metabolized. Now let me move on to renin inhibitors. Renin inhibitors are also designed as peptidomimetics, so they're designed to mimic the sequence of angiotensinogen that is actually recognized by renin. Okay, and here is the structure. Here is the sequence that is recognized by renin. So it uses a non-peptide template. And then it puts the amino acid that are needed to mimic the sequence. I will not go through the same exercise that I went through with the ARBs to show you which amino acid is represented here. But when you look at the structure, you can infer which amino acids are represented. And I will not quiz you specifically on that for aliskiren. Now the mechanism of action here, aliskiren is going to both inhibit the formation of angiotensin 1 and angiotensin 2 because it's going to block the hydrolysis of angiotensinogen. Okay, it's going to block the hydrolysis of angiotensinogen by renin. It doesn't cause any compensatory increase of renin in the plasma, so there is no synthesis of additional renin in the plasma. In the structure-activity relationship, structure-activity relationship has to deal with how do we compare a particular drug with other drugs, and how do we make changes to the structure that improve or decrease the activity. So in the case of the renin inhibitors, there's not enough compounds on the market to be able to compare the activity of the drugs with the structure. So there is not a lot of data. That's why this area is empty. Now this compound is available as it's a basic compound. It's available as a salt, which allows it to be very water soluble. Okay, and high fat meals are going to decrease the absorption of the drug. Now for the metabolism, it's excreted 90% unchanged, but you can have a dimethylation that will lead to the formation of an alcohol. So you could have dimethylation here actually that could lead to the formation of an alcohol. And I'm not actually showing the metabolite here. So what do I want you to remember from this? What I want you to remember is the fact that it mimics the sequence of angiotensinogen that is recognized by renin. Okay, I want you to remember that this drug's mechanism of action causes it to inhibit both the formation of angiotensin 1 and angiotensin 2 because it blocks the hydrolysis of renin. And I want you to remember that as far as structure-activity relationship, there is not enough data for a thorough discussion there, okay? So what did we learn today? Today we took a look at drugs that affect the renin-angiotensin pathway for the purpose of the treatment of hypertension. For each of the drugs, we've taken a look at their mechanism of action. We have explained some of the structure-activity relationships that are present between the drug molecules and the receptors. And then we focused on key structural components of ACE, ARBs, and renin inhibitors. Okay, thank you for your attention, and I hope you have a good rest of your day. Thank you.